friends, in this video we are going to study the block diagram of digital storage oscilloscope, also known as DSO. In the block diagram, first we will study the block diagram of a basic digital storage oscilloscope, explaining the functions of all the elements present in the block diagram. So let us start with our topic. Now, as the digital storage oscilloscope, it is an instrument which gives us the storage of a digital form, or it is going to give us the digital copy of the waveform, and it allows us to store the signal or the waveform in the digital format in the digital memory, and also it allows us to do the digital signal processing techniques over that signal. So oscilloscope, as it gives us the visual display of the waveforms. So digital storage oscilloscope, what it does, it accepts an analog signal. It is going to convert that analog signal into a digital signal, store it in the digital memory, and then it is going to convert that signal again into the analog form and display it over the screen. So if we see the block diagram of a basic digital storage oscilloscope, it will be like, first we will have the input signal. So this is the block diagram of a basic digital storage oscilloscope. In this you can see that the digital oscilloscope, it is going to first digitize the input signal. The input signal is first amplified. If it is having any weak signal, so it is going to be amplify it. Then it is going to digitize that input signal, means analog signal will be converted into a digital signal. We are using a digitizer like an A to D converter will be used. After that, this digital signal will be stored in the memory, which is the digital memory. After that, we are having the analyzer circuit, which are going to process the digital signal. Okay, after doing the processing, the waveform is reconstructed, means again the digital signal is converted into the analog form, and then that signal will be applied to the vertical plates of the cathode ray tube. Okay, now we are having two inputs to the cathode ray tube. One is the vertical input and second is the horizontal input. Because in CRO, we are the digital storage oscilloscopes, we are plotting the 2D graph of the signal. Means we are having a y-axis and an x-axis. So two inputs will be there. One will be the vertical input, that is the y-axis input, and second is the horizontal input, that is the x-axis input. So here the x-axis input is the horizontal input, and which is an internally generated time-based signal. Now this circuit, time-based circuit, it will be triggered by the input signal. Okay, also there is a clock input. Both are going to trigger this time-based circuit, so it is going to generate the time-based signal, which is a ramp signal. Then the signal is amplified by the horizontal amplifier, and this horizontal amplifier will provide the input to the horizontal plates. So on the CRT screen, that is cathode ray tube screen, we will get the waveform of the input signal versus time. So on x-axis we will have time, and on y-axis suppose the input signal is a voltage, so here we will have a voltage. So this is about the block diagram of a basic digital storage oscilloscope where an amplifier, digitizer, memory and the time-based circuitry is used. Now if we talk about the more complex block diagram of a digital, or we can say more widely described block diagram of a digital storage oscilloscope, it will be like this. Okay, so here you can see that we are having an input signal. Okay, then we are having the attenuator and the amplifier stages, which are going to attenuate if any noises are present in the signal, and then we are having a amplifier here. Then a sample and hold circuitry is used, okay, which is going to sample the analog signal. This sample and hold signal, it is going to do the sampling of the analog signal so that it can be converted into the digital form. Okay, after that we are having an analog to digital conversion. Okay, then memory, so that digital signal will be stored in the memory, data in and data out. Now after coming out of the memory, this will be a digital signal. So here we are having a D2A converter which is going to convert the signal again into the analog form. Then we have the vertical deflection amplifier which is going to amplify the signal and then given to the vertical plates of the cathode ray tube. Here we are having the triggering circuit which is given to the control logic. This control logic is going to trigger the sampling of the signal. Also this control logic is going to produce the time-based signal, and this signal is a digital signal again. Okay, control logic means here we can use a microprocessor, okay, which is going to do all the control logics in the circuit. So this is going to produce a digital signal which is further converted into an analog, then amplified by the amplifier and given to the horizontal plates of the CRT. So if we describe this block diagram, it will be like, so in the first part of the block diagram, the input signal, it is given to the attenuator and the amplifier section. This is just like same as what is done in the conventional oscilloscopes where we are having the amplifier and the attenuator, which is going to amplify the signal if it is very weak signal, but it is not going to distort the signal. Okay, no modifications will be done, only amplification of weak signal will be done in this part. So first the attenuator is there. So after coming out of the input attenuator, we will have the attenuated signal. This attenuated signal is then given to the vertical amplifier which is going to amplify it, and after the vertical amplifier it is given to the analog to digital converter. You can see in the block diagram that after coming out of the vertical amplifier, it is given to the analog to digital converter. And this analog to digital converter is going to convert the analog signal into the digital signal by using this sample and hold circuit. This sample and hold circuit is going to perform the sampling over the analog signal. So this analog and digital converter, it is going to digitize the analog signal and it is going to create a data set which is then stored in the memory. So the output of the A to D converter is stored in the memory. It is data in and data out. Now this data set which is present in the memory, it is processed by the microprocessor. Okay, you can see here the control logic is the microprocessor. So here this microprocessor, it is controlling the sample and hold circuit also, and also it is giving the control signals to A to D converter and memory. So input is the read and write, like if we want to do any processing over that data, that can also be done, and the output of this memory is given to then the digital to analog converter. So this A to D converter, it creates a data set which is stored in memory, and data set is processed by the microprocessor. So digital is converted into analog, then it is amplified and given to the vertical deflection plates of CRT. Similarly, the control logic microprocessor, it is producing the digital output. Okay, means we can say that time-based signal is produced. And this time-based signal, it is a digital signal, it is a ramp signal, so it will be converted into analog form, amplified, and where it is given to the horizontal plates of the CRT. So this is how all the blocks, their functions are described in the block diagram and how they works. Okay, now the digital storage oscilloscope, it can work in 3 modes of operations. One is the roll mode, second is store mode, and third is hold or save mode. So these are the 3 modes of operations of the digital storage oscilloscope. In the roll mode, very fast varying signals, they are displayed on the display screen. In the store mode, the signals waveforms, they are stored in the memory, and in hold or save mode, some part of the signal will be hold for some time instant, and then they will be stored in the memory. So these are the 3 modes of operations of the DSO. Now in the DSO, we have seen that the digitizing of the signal is done. An input signal, it will be digitized, it will be converted into the digital form. So how this digitizing is done, let's see. Now digitizing is done by taking a sample of the input waveform at periodic intervals. What we do in the sampling. So in sampling, what we do that at certain time intervals, we are going to pick the value of the input waveform. So if we diagrammatically represent the digitizing or the sampling process, it will be so at the periodic intervals of time, like at this here, A, B, C, D and E. So at the periodic time intervals means when one and half means when half of the time cycle is completed, then we are taking the samples of the signal. Okay. Now at these instances, when we are taking the samples of the signal, these values, so these are the digital form of that signals. Now this process of digitizing or sampling, it should follow the sampling theorem. The sampling theorem says that the rate at which these samples are taken, this rate should be greater than twice the frequency, the highest frequency present in the signal. What the sampling theorem is? So the sampling theorem says that the rate at which the sampling is done, it should be at least greater than twice the highest frequency present in the input signal. Now when this condition is not satisfied, then an effect called aliasing occurs in the signal. Okay, means that the analog signal is not properly converted into a digital signal, and this effect is called the aliasing. Okay, now if we want that the sampling rate, it should be at least twice as fast as the highest frequency. If this condition is satisfied, then the resolution of the A to D converter is decreased. So if any changes are made in the sampling rate, then the resolution of the A to D converter is decreased. And due to this reason, we can say that the bandwidth and the resolution of the A to D converter and the oscilloscope, it is affected. Okay, so due to this reason, what is done, we are going to make some changes in the block diagram of the digital storage oscilloscope. We are going to add an analog store in it. Okay, so when the signals, they are amplified, they will be stored in the analog store. After that, they will be digitized, and then they will be stored in a digital store. Okay, so this is going to reduce the problem, or it is going to eliminate the problem which is caused due to this aliasing and due to the decrease in the resolution of the A to D converter due to an increase in the sampling rate. Okay, so the modification which is done in the block diagram, it will be like this. Here we are having the channel 1 and channel 2. We are having two input signals. For channel 1, we will have a separate amplifier. For channel 2, we are having separate amplifier. So separate amplifiers for the channel 1 and channel 2. After that, we are having an analog store. Okay, so these signals, after amplification, they will be stored in the analog store. After that, they will be given to the analog to digital converter. So this reduces the problem that if we are increasing the sampling rate, the resolution of the analog to digital converter is decreasing. Okay, here we are using a multiplexer, so whatever signal we want to give to the CRT, that will be chosen by this multiplexer. After this, we are having a digital store. So after the conversion, the digital signal will be stored in the digital store. Then we have digital to analog converter, which is going to convert this signal again into analog form with the help of this dot joining process. Then this signal will be amplified and given to the vertical deflection plates. Again, this circuit will be same. Here we have the time based circuit, which is also multiplexed with this vertical signal. Okay, then we have digital to analog converter, which is going to convert it into analog signal, amplify it, and provide it to the horizontal deflection plates. So this modification, that in addition of analog store and a digital store, is done in the block diagram of the digital storage oscilloscope, so that the problem that resolution of the A to D converter is decreased with an increase in the sampling rate will be eliminated. So input signals first amplified, then stored in analog store registers. So due to the storage in these registers, they can be read out at a much slower rate by the A to D converter. Then the digital output of the A to D converter, it is stored in the digital store. So it is going to allow 100 mega samples per second. Okay, but it is going to give us the advantage that now the resolution will not be decreased, but there will be a disadvantage that due to this, the oscilloscope, it will not be able to read the signal while it is digitizing it. Okay, while the digitizing process is going on, the oscilloscope, it is not going to read the signal. So due to that problem, the a blind spot will be created on the screen of the oscilloscope, and that is the disadvantage of this analog store procedure. Now in the block diagram, you have seen that we have used a multiplexer after the analog store also, and after this digital store. So if we want that any of the channel, there are multiple channels which can be connected with the oscilloscopes. So those different channels, they can be selected with the help of this multiplexer. Okay, so many number of channels can be used. Now, when this analog signal is converted into digital form, it is again converted into analog form so that it can be displayed on the screen of the CRT. So this reconstruction of the waveform is done by the dot joining process. Okay, so let's see that how this waveform is reconstructed and displayed on the CRT screen. Now, as we have studied that the if we want that proper sampling of the analog signal is done, then we have to use the sampling theorem that our sampling rate should be at least twice, at least greater than twice the highest frequency present in the input signal. Now, even if we have make the sampling rate equal to twice the highest frequency, then also aliasing can occur in the signal. Like if the output it is present in the form of dots, then also the aliasing can occur. Let's see how. Suppose this is our signal which is present in the form of dots. So when this output signal, okay, this is a digital signal, we want that an analog signal should be generated from this. So there are two types of reconstruction. One way is to join all these dots by a straight line. Okay. Another way is we can form a sinusoidal signal. Okay. So in this way also there are two types of reconstruction, that how the waveform can be reconstructed from the dots, from the digital output which is in the form of dots. So there are two types of formation: linear interpolation and sinusoidal interpolation. So in the linear interpolation, the dots, they are joined by a straight line. Whereas in the sinusoidal interpolation, the dots, they are joined by a sine wave. So these are the two ways in which the waveform can be reconstructed, means it can be converted into the digital form to the analog form. So in this video, we studied the block diagram of the digital storage oscilloscope. First, we studied the basic block diagram, in which we studied that we are having an amplifier, then a digitizer, a memory, and then we have the CRT. So time-based circuitry is different, which is producing the time-based circuit, and input signal is then first converted into the digital form. After that, it is again converted into analog form. Waveform is reconstructed and it is displayed on the CRT screen. Then we studied that there is a problem in it, that the sampling frequency, it should be twice the highest frequency present in the signal. Aliasing is caused, and to remove this aliasing, we have to increase the sampling rate. So when we are increasing the sampling rate, the A to D converter, the resolution and the bandwidth of the oscilloscope, it is decreasing. So to eliminate the effect of the aliasing or eliminate the effect of increasing the sampling rate, we are introducing the analog store and the digital store in the block diagram. And this analog and digital store, it is giving us the advantage that the resolution is not decreased when we are changing the sampling rate. After that, we studied that how the waveform is reconstructed using the dot joining process in the block diagram. So this is the complete description of the block diagram, explaining the functions of each block present in the block diagram. So I hope that this topic, block diagram of a digital storage oscilloscope, is now clear to you. Thank you.